All right, let's go and get started. Just so everybody's aware, I'm dealing with I don't know if it's a stomach bug or I don't know if it's like I ate some bad food or something yesterday, but I'm not firing on all cylinders today. So if I'm going a little slow, please bear with me. Sign-in sheet is going around, so let's take care of some housekeeping. Number one, you've got your homework due on Friday. Okay, so. Any questions? I know most of you have a concrete exam. I'm aware. We're actually, in here we're actually doing pretty good on progress. The water hammer. Funny guy. The only other thing I'll mention, there are alignment charts on the huddle station outside my office, so if you all need any extras, you can just go up and grab them whenever you have time. And again, I've been making it a point to put the homework schedule from here on out on the slides. As far as I know, that is our homework schedule. So that way you won't be surprised when I assign something. Oh, it's due Friday. What? Yeah. So now everybody's got that down. Any questions? All right. I know many of you have a concrete exam here in an hour, and I know you're probably thinking about that. Fortunately, the lecture that we're doing today is pretty simple. It's not it's not very challenging from a computational standpoint, and even from a lookup standpoint. This is pretty simple. Today, what we're going to do is we're going to dive back into continuously braced beams. We're going to finish our example on analysis, and then we're going to do one on design. And again, I think you'll find this is pretty simple. So fortunately, it's a task that you can pick up pretty easily, especially if you've got other things on your mind like a celebration coming up in about an hour. Whew. Okay. So last time we looked at the ZX chart. It's one of the most important design charts we will use for beams, period. One thing that I should point out, a lot of this design chart we're not using right now. Okay, we will later. For instance, we're not using FEMR right now. We're not using LP or LR right now. We're not using our beam factors now. We will later. Okay, so just so you are aware, we're doing continuously braced beams right now. When we do discretely braced beams, we will be using this design aid again, so just something you need to be made aware of. And we talked about why some of the values are bold, and those are the lightest ones within a given chunk, a given group. So in design mode, you're going to want to use those if you can. Sometimes you love to use a W30 by, W30 by 116, and then you've only got 24 inches of room because the architect said you only got 24 inches to insert that beam. So you might end up having to go with something like a W24 by 131. Even though it's heavier, the architect didn't give you the 30 inches of room necessary. So you see what I mean? There's something to keep in mind. All right, so deflections. We mentioned deflections last time. We said that deflections, unlike concrete design, deflections aren't really codified in the spec. They are listed in some design guides, and we will we at least talked about these last time, like your vertical deflection in a floor beam or girder for a partition finish is going to be either L/360, to a 1-inch maximum on half your live load or something like that. So just make sure that you're aware of this stuff. Again, for the problems that we do in this course, just to keep everything straightforward, I'm just going to give you the deflection limit, which isn't really that far off from what you would see in practice anyways. I mean, keep in mind, your client the architect, the engineer, they all have to come to that agreement at the beginning. So you'll know what the deflection limits are because you'll know that before you begin your project. Sound good? Okay. So if you need to select a beam based on deflection, you have the IX tables as opposed to the ZX tables. They're a lot simpler in layouts, literally just listing every beam by moment of inertia, and then again doing the same thing that we did before. Anytime that you have a lighter shape, break that up into a separate chunk, and then the top row is bolded. Same reason for the IX tables. Sound good? Okay. So this is the problem that we were looking at last time. We had a W16 by 31. We had 450 pounds per foot that wasn't including the beam self-weight. So how heavy was the beam? Say it again. 31 pounds per foot. It's a W16 by 31. That's what the 31 means. It's 31 pounds per foot. Dead load of 450 pounds per foot superimposed. Live load of 550 pounds per foot, and the beam was 30 foot long. Okay, so we're going to calculate the moment capacity. We're going to look up the shear capacity, and then we're going to check this beam based on a service live load deflection limit of L over 360. So some of this I think we kind of just roughed out near the end, but I think we're going to try and do it a little more formally. So where are we at? Okay. So this is where we left off last time. We have a dead load of 450 pounds per foot, a self weight of 31, and a live load of 550. So we factor that, incorporating that, that self weight, we get about 1,457 pounds per foot. So WL squared over 8 and WL over 2 give us our moment and shear. Sound good? Now I want everybody to be clear on a couple things that you see in these tables so that you're aware where this stuff comes from. Okay, so let's look at the W16 by 31. All right, first off, what is the ZX for a W16 by 31? Now you can look that up either in table 1.1 or in the ZX charts. It doesn't really matter. There we go. And while we're at it, what is our IX going to be? There we go. Okay. So just so everybody's aware, because this beam is continuously braced, our moment capacity can be computed as phi Fy ZX. Okay. Now Fy we're going to take to be 50 KSI, and again, that's sort of the general policy from here on out, that unless otherwise noted, 50 KSI. I mean, we've been dealing with wide flanges only, for instance, just with columns. It's going to be the same thing with beams. Okay, so our phi value for bending, does anybody remember what that is? We talked about that last time. Anybody remember? Nope. 0.9. All right, 50 KSI. And 54.0 cubic inches. So what does that come out to be? Just so everybody's aware. Say it again. Do I have a second on that? Okay, now what are the units? Inch kips. So in foot kips, what would it be? Say it again. Okay. So that's if you went and calculated your moment capacity. Now note, from, oh goodness, getting ahead of myself. from table 3-2, help me out. What was this? 203. Foot kips. So is everybody seeing, how they're getting that value? I mean, that's just the plastic moment. Plastic moment is FYZX and then factored 0.9. The difference between the two is just rounding, okay? And for 50 KSI steel, I have no problem with you just looking up the capacity. There's nothing wrong with that. The big thing I really, really want to be clear is that this capacity is the capacity assuming continuous bracing. In other words, that there's no discretely braced segments, like you've got cross frames every 15, 20 feet or something like that, okay? When you've got cross frames and you've got to account for a discretely braced section, computing the capacity is a tad more involved. It's not terribly difficult, it's just a little more involved. So it's just something I want you to be aware of. The capacity for a continuously braced beam is really simple. It's just BFYZX. For discretely braced, a little more goes into it. Sound good? Now, while we're at it, what is this? The shear capacity, in other words. Say it again. 131 kips, right? So compare that against the load. Like, what's the shear load? 21. So it just blows shear out of the water, okay? And that is not that uncommon of a finding in beams. In fact, more often than not, that's what you're going to find. You're going to find a crazy shear capacity compared to the load. Because with steel beams in buildings, you're really not designing them for shear. You're designing them either for moment or deflection, okay? Speaking of, let's look at deflection, okay? So, excuse me. It'll be like that, right? Did you really say that? Oh, I needed that. For those of you who came in a little late, apologies if I'm going a little slow. I'm getting over a stomach bug, so yeah. All right. Deflections. Let's start off with our deflection calc. Now, we are comparing, or we are evaluating this beam for what type of deflections? Dead load deflections, live load deflection. And what did you say? Service live load deflections. In other words, no load factors, okay? No load factors. So our load, let's get everything into consistent units, okay? So this is 0.55 kips per foot. Now how many, 0.55 kips per foot. How many kips is that per inch? I think you went backwards. 0.0458. Okay. Now the beam is 30 foot long or 360 inches long, right? Now what's E? That's right. E is 29,000 KSI. That's right. And then we have IX is 375 inches to the fourth. So, what do we have? We have a simply supported beam and we have a uniformly distributed load. So how do we compute the deflection? If you don't remember, there we go. And it's in the manual, all right? So I think I'm going to be cramming this. I'm going to move this on to the next slide. Does everybody have this? Excuse me. Excuse me. Everybody got this? Okay. 20. Okay, so therefore, the deflection due to the live load is 5W L to the fourth over 384 EI. We're going to do I sub x since we're bending about strong axis. That's typically the way you bend beams anyways. So 5, what was it, 0.0458, is that what you said? .360 inches to the fourth divided by 384, 29,000 KSI. It was 375, wasn't it? Goodness. All right, so tell me what you get. What's it? That is an absolutely great wonderful question. Why can you just compute the live load deflection as opposed to concrete design? What's that? Well, yeah. But somebody kind of answered it. No cracking. Exactly. No cracking. There's no change in I. Exactly. Well, you can get, well, let's put it like this. If a steel beam cracks, which it can, it has nothing to do with deflection. It has to do with fatigue. Under repeated loadings, you can develop a crack in the beam. It's kind of like if you take a paper clip and you bend it back and forth, what happens to the paper clip right there at that bend? It just sort of gives up, right? Well, that's kind of what happens under fatigue loading. So. Now, what's the limit? What's the maximum deflection? Are we good? So based on the numbers, what do you think actually governed the design of this beam? Was it the moment or was it the deflection? I mean, it certainly wasn't the shear. Yeah, it probably was. I mean, what do we have? We had a moment of 165 and a capacity of 203. What's 165 divided by 203? So under bending, that's a performance ratio of 0.8 something, bless you. And what's it under deflection? It's like 0.92. So actually the deflection governed this beam. In other words, the beam is strong. I mean, the capacity wasn't the issue. It was the deflection limits. Okay? Make sense? Well, yeah. You're right. Yeah, but I mean, I'm just trying to get, for like, if we were in design mode, that's what would govern. Make sense? Okay. The delta? Okay. That's true, and we brought that up before. You can account for dead load deflection by cambering your beam. Remember, you can bend it upwards, sit down, then set the dead load on it, then it sits flat. The live load is the only deflection that the user or the occupant is going to notice. Does that make sense? That's a good question, though, and that's something everybody should be aware of. Everybody good? Okay. The only other thing I want to do is I do want to check compactness. Excuse me. No. Although, nice reference. All right, help me out. What is, let's see if you all remember this. Do you all remember where to find these? Oh, I know. What, they're in one of the tabs. What's that? Say it again. 16.1-17. Okay. Now, since we're looking at this table for the first time, let's start off with you, Caleb. What's the lambda PF going to be that we're going to use? Yeah, I want you to read the table and see it. That's why I'm bringing it up. The top one? No. Lambda, remember, a flange is unstiffened. It's only supported on one side. A web is stiffened. It's supported on both. So what case? Case 10. They should be tabbed from the column sections. Like, you should already have a tab there. And what was the limit? What was the value? All right. Is everybody able to find that? And we're going off of case 10. Is everybody able to find that? And everybody know why I'm calling that the flange limit, because it's unstiffened. All right. While we're at it, what's it going to be for the web? Case 15. Hold on. And what do you have? Is everybody able to find that? That's important. All right. So let's do some plugging and chugging. What do we got for this? 90.55. Okay. Now, does anybody remember what we compare these against? Remember, the top one you compare against BF over 2TF. This one's H over TW. So what do we get? Does anybody remember where to find these? There we go, table 1-1. .28 and H over TW. All right, does everybody know where we're finding that? Table 1-1 for the 16/31, the W 16/31. Now, does that mean our shape is good or bad? This is good, okay? Look, here is a compact shape. Now here's a slender shape. See the difference? Okay. So this compact shape over here, these elements are not very slender, right? Make sense? These are a measure of the slenderness of this and this. Sound good? Okay. These are how slender our section really is. These are the limits. Okay? Make sense? So, because our actual slenderness is smaller than our limits, we have a compact shape and we're good. What? Okay, remember, if you're not good, that does not mean that if you place a feather on the beam, it explodes. That just means you have to use a different section of the specification in order to determine the capacity. In other words, 0.9 FYZX probably won't be your capacity. It'll be a more involved expression, which we'll talk about that stuff as we move on. Sound good? All right. Any questions about this? This is really important. Well, the chapter E is for columns. You'd be using like F point whatever, because F's for beams. Yeah. But you are right. You would just be using a different section. Sound good? Okay. Well, if you understand that, then design is pretty straightforward. Okay, so if you want to design a continuously braced beam, you start off determining the factored moment. I have here determined the required ZX. I'm not sure that that's necessary if you know that you're dealing with 50 KSI steel. Since the guide is for 50 KSI steel, you could literally just look up the phi MP and be good. So you can skip that step if you know you're dealing with 50 KSI steel. If not, then you would need to look it up. Look up that section based on moment requirements, and then update your loads if necessary. So, you know, if you assume 50 pounds per foot and your beam weighs 200 pounds per foot, you need to go through and update your loads. But other than that, it's pretty straightforward. If you find that deflections are likely to govern your design, then go to table 3.3. And don't worry, we'll have a couple examples on this. Again, I think you're going to find this is pretty straightforward. Sound good? All right. Let's then look at this. Okay. So let's design a beam that's simply supported. Now, let me be clear. If the beam was not simply supported, if it was cantilevered or overhanging or something like that, the only thing that would affect us right now is our structural analysis. We just have different moment formula. We wouldn't be using WL squared over 8. We'd be using something else, or maybe we just need to draw the moment diagram. Sound good? Okay. So the beam has continuous lateral support, so we don't have to worry about beam buckling. We'll worry about that later. It has 400 pounds per foot of dead load, not including the beam self-weight, so that means we're going to have to assume a value. And then we have a live load of 800 pounds per foot. Now, this is a really long beam. This is a 60-foot long beam. So this is long. Okay, so we're going to do this problem for 2 cases. So what I mean by that is we're actually going to, you can sort of treat this as if we're doing 2 problems, like a 21A and a 21B. We're doing 2 different design problems. One design problem, we're not going to consider any deflection limits, and the other one, we are. Okay, so yeah. Sound good? Okay. All right. So first thing that we need to do is our factored moments. Excuse me. Now, what do we not know in order to determine our factored moments? Self-weight. So we got to assume a value. So what I'm going to do is this. I'm going to assume a self-weight of 100 pounds per foot. Okay? Excuse me. So we know that our dead load is 400 pounds per foot, or 0.4 kips per foot. And our live load was, what was that, 8? Whew, excuse me. So therefore, our factored load got to add that self-weight. Whew. Okay, so what do we got for this? 1.88. Do I have a second on that? Okay, good. Try to stand up for a little bit. So therefore, our bending moment is that times the length of 60 feet. 60 feet, not 6 feet. Put up here, now it's 60 feet. Whew. Say it again. All right, do I have a second on that? All right. Whew, goodness, sorry. Any questions? Okay, now, so we're going to do this problem twice. The first one we're going to do is case 1. No deflection limits. Now, because we have a beam that is continuously braced, we know that its capacity is phi MP, okay? Now, we know that it's 50 KSI, so here's how this is going to work. I want you to go to the ZX tables, okay? I want you to find the lightest shape that has a capacity of at least 846 or more. Remember, lightest shape. So bold row. W12 by 84? Sorry, W27 by 84. Okay, does anybody else seconding that? Okay. So, now, you chose that because of what? A phi MP of what? Okay. Sound good? Now, let me ask you this. Do we technically need to update our moments? Think about it. Now, you're saying no, you're saying yeah. Why are you saying yes? But check what? Hold on. What were you going to say? Or there you go. The beam, we assumed that the beam weighs 100 pounds per foot. It does not weigh 100 pounds per foot. It weighs 84. So we could stop right now. Yes. It's funny you mentioned that. Let's see. Let's see this. It's like I've got a plan or something, isn't it? Let's go through and update our moments. One of the telltale signs that you probably should do this is look at these two numbers. I mean, we got a lot of capacity to work with, right? I mean, this is 846. This wasn't like 847. It's like 915. We got a little bit of room to work with. So it might be worthwhile. So let's update our loads. So what is W sub U? Here, I'm just going to do the values. Instead of 0.1, it's 0.084. Does everybody see where I'm getting at? What does that come out to be? .86, a little lower. MU here, I'll just plug it in. So what do we got here? 837. So that moment went down a little bit, right? Does that mean we could probably pick another section? And what section would that be? Bless you. W24 by 84. So redesign. Now, it weighs the exact same, so do we update our moments? No, the moments are going to be the same. What is the advantage, though, using this section over that section? It's shallower, right? And if it's the same hit to our wallet, but it gives the architect 3 more inches of floor space, well, let's use it, okay? So this case 1 has no deflection limits, right? There's no deflection limits. Why did you pick the W24 by 84? What is its PMP? Okay. We know it meets moment requirements, right? There are no deflection requirements. What's left? Well, there's compactness. I'm going to skip the compactness for this, but to be thorough, there's one thing we ought to check, shear. We should automatically go ahead and check the shear. Even though it's not going to govern, what is the shear capacity? Bless you. Now we compare that against the factored load, okay? All right? The factored load is WUL over 2, right? That's the maximum shear on a simply supported beam, right? Okay. So plug and chug. Bless you. What do we get? Are we good on shear? Barely, right? Again, shear doesn't really affect design of steel beams. It's moment, okay? And I mean, look at our performance ratio that we're getting for moment. I mean, we have a moment of 837 applied, a capacity of 840. So, I mean, we're right there. But the shear is just through the roof. So, case one. All right. Any questions? All right. Let's do the deflections, and then I think we'll call it. Actually, let's see what time it is. Yeah, I think we can knock that out. What's that? I know. Hey, now. Does everybody have all this? Let me tell you. See, where I come from, we call that sass. I'm just saying. All right, everybody got all this? Okay, all right. Now, case 2 has a maximum live load deflection of what? L over 500. All right. So it would be wonderful if I could just use the beam that I used previously. Okay, it'd be great. The problem is that I don't know if it's going to meet deflection requirements. Now, there's an easy way of going about that, and that's doing a little bit of algebra. Yes? Well, the room doesn't really matter. It's the moment of inertia. No, because no. Here's why that doesn't matter. We're designing the new Geico Insurance corporate headquarters, right? Do you think John Q. Public is going to care about the depth of the beam when they walk onto the 12th floor and it's deflecting too much? You see what I mean? The deflection is, here's the floor, it's flat, how much is it sagging? So it's actually independent of the beam that we use. The idea is that we are selecting a beam that's stiff enough to resist those deflections. Now that's really not what we're interested in. What we're more interested in is if I'm standing here, like if I'm standing here and the floor is going like that. That I would not like to have happen. No, but seriously, that's what we're after. Does that make sense? You're saying that the floor beam would hit something. I'm saying the entire floor system would deflect. That's what we're talking about. What's that? That is a way of over-countering or getting dead load deflections taken care of. It's just pouring, over-pouring in the center so that it's flat. That's dead load. That's not live load. Well, there's a steady state though. There's a steady state. All right. I tell you what. It's 9:45. I think we'll tackle this next time. if that's okay. I'm good. What's that? Yeah, we'll stop it for now. We'll pick this up on Friday.